we're going to learn how to find and apply related rates in order to solve real life problems. Related rates stems from the chain rule, and we're able to use it to relate variables that are changing with respect to time, which is a lot of situations in life. If you consider a tank, say we have a tank that's shaped like a cone, and we have water on the inside of this tank. So let's say that it starts off being completely full and that there's a leak at the bottom. So as it's leaking, it's eventually going to be at this height, and then eventually it'll drain some more and it'll drop to that height. So as time changes, as time goes by, there are things that are changing. And with things that are changing, we are able to talk about the derivative. So what's actually changing here? Well, a few things are changing. The radius of the water is changing. The radius right here is larger than the radius here. The height of the water is also changing. The height here is different than the height here. Also, the volume of the water, how much space all of that water takes up, is different than how much space all of this water takes up. So we do have an equation that relates the volume, the radius, and the height. This equation is specific for a cone. Now keep in mind, as we go and we start working problems, we might not always be working with a cone. We might be working with a sphere or a cube or a triangle or a square that's changing in size. So remember that we're not always working with a cone. It doesn't have to be a 3D shape. Okay. But this equation is specifically for a cone. So if I want to find out information about how the radius, the height, and the volume changing is all affected, I am going to come in and take the derivative of both sides of this equation. But everything is changing with respect to time, and so we are going to come in and take the derivative with respect to time. Now notice here on the right side of the equation, as I'm applying the derivative operator, we do have a coefficient, a constant coefficient of pi over 3. So I'm going to go ahead and pull that on the outside of this derivative operator. Remember that we did talk about things that were changing over time. Variables that are changing over time in this case were the radius, the height, and the volume. Now, please do distinguish that when I say height, I am talking about the height of the water, not the height of the cone, because the height of the cone never changes, right? We are specifically talking about the height of the water and the radius of the water. So let's come in and take the derivative on both sides. ddt of the volume is simply dv dt, the derivative of whatever the volume. On the right side of the equation, we will have this constant pi over 3 in front, but we will need to come in and use the product rule to take the derivative of r squared h, because we have those two things being multiplied together. Here is where we need to be making sure that we are applying the chain rule, because the derivative of r squared, we're going to take the 2, exponent of 2, and bring that down to get a 2r. But remember, this was not x, this was r. And r is changing over time, which means that r has a derivative. It is dr dt. Now to take g prime, we want to take the derivative of h, but h is changing over time. So h has a derivative, and it is dh dt. So now that we have all four of those pieces, we can apply f prime g plus g prime f to finish getting the derivative using the product rule. So here is our f prime g, and to this we will add g prime f. And now we have an equation that tells us how all of these different changing rates are related to each other. Related. Notice that the rate of change of the volume, which is decreasing in this case if water is leaking out of this, the rate of change of the volume depends on both how fast the radius is changing and how fast the height is changing. It also depends on what the radius is at that particular moment in time and what the height is at that particular moment in time. And that's another good way to think about these related rates equations, is that we are dealing with things over time. So this equation is true at every particular moment in time. So you'll notice in these problems that they ask us to find something at a certain moment in time, and that's going to determine what values we would plug in for all these different variables here. In example 1, we again have a tank that is shaped like a cone. Here they tell us that the height of the water level is changing. So this, I do know that the height is decreasing because the derivative is negative, changing at a rate of negative 0.2 feet per minute. And the radius is changing at a rate of negative 0.1 feet per minute. We are being asked, what is the rate of change of the volume? So automatically I know that we want the rate of change of the volume. Rate of change means derivative, and I want the derivative of the volume. So I want dv dt, and I want it particularly when the radius is 1 foot and the height is 2. So I want this when r is equal to 1 and h is equal to 2. Well, lucky for us, up here we did find an equation for dv dt by taking the derivative of the volume formula. So now I am going to be plugging in r is equal to 1 and h is equal to 2. We also have values to plug in for dr dt and dh dt now, because they tell us that the height of the water level is changing at a rate of negative 0.2. The height is changing at a rate. Rates are derivatives. So we know that dh dt, the rate of change of the height, is negative 0.2. They also told us that dr dt, the rate of change of the radius, was negative 0.1. So now we have values to plug in to this entire equation. We still have the pi over 3 in front. There's the 2. For the r, we are going to be plugging in 1, and for the h, we're going to be plugging in 2. We're going to replace dr dt with negative 1/10. We add r is equal to 1, and dh dt we are replacing with negative 0.2. This leaves us with negative 0.2 pi, or negative pi over 5. And the answer to this last question here in example 1 is yes, and we already discussed that. And an explanation of that is simply this equation. That equation, which gives us the rate of change of the volume, clearly depends on the values of r and h. Example 2 tells us that the variables x and y are both differentiable functions of t, which automatically tells us that we will have a dy dt and a dx dt. They go on to tell us that these variables are related by the equation y is equal to x squared plus 3. We're being asked to find dy dt when x is equal to 1, and we're given some extra information that dx dt is 2 when x is equal to 1. So to find dy dt, I first have to get my hands on dy dt. So we're going to come in and we're going to apply the derivative operator with respect to t to both sides of this equation. Taking the derivative now, the derivative of y is dy dt. We're going to need to use the generalized power rule to take the derivative of x squared. We'll bring our exponent of 2 down. New exponent on x is 1. Chain rule says we have to multiply by the derivative of x, but in this case, the derivative of x is not 1. It is just dx dt. X is a changing variable. And the derivative of 3 is simply 0. So we want dy dt, and we have dy dt equals. We want it when x is equal to 1. So I'm going to now plug in these values when x is equal to 1, that same notation with a vertical bar. Plug in 1 for x, and then for dx dt, we have additional information that again, when x is 1, dx dt is equal to 2. So we are able to get our final answer of 4. In example 3, we have that a pebble is dropped into a pond, causing ripples to form concentric circles. So we have a situation that looks like this. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. That sentence right there, that the radius of the outer ripple is increasing at a constant rate of 1 foot per second. Well, it's talking about the outermost ripple here. And they tell us the rate that it is increasing. So the rate tells us that this is a derivative. They have given us the derivative of the radius, the rate of change of the radius. It is 1 foot per second. Then they go on to say when the radius is 4 feet, at what rate is the total area of the disturbed water changing? So it's a good thing that we have the outer radius there, because that's going to give us the total area of the disturbed water. When the radius is 4 feet, what rate is the total area changing? So what we want in this problem is the rate of the area. We want the derivative of the area. The derivative is rate. And we want to know what the derivative of the area is. How fast is the area changing when the radius is 4 feet? And so in order to find the ADT, and I'll just go over here and jot down that we were given earlier in the problem that the RDT is equal to 1. And I will put units on this because I think it will help us understand what's going on here. This dRdt is 1 feet per second, 1 foot per second. So I'm going to start with the formula for the area of a circle, because that's what we're talking about in this problem, the area of a circle. And we're going to come in and take the derivative of both sides with respect to t. The derivative of a is simply dA dt. On the right side, we have that constant of pi in front. We'll need to use the power rule to take the derivative of r squared. I'll bring the exponent of 2 down. The new exponent on r is 1. The chain rule says I pick up a dr dt. I would like to know what dA dt is at a certain moment in time, in particular at the moment in time when the radius is 4 feet. So I'm going to go ahead and plug in a radius of 4 feet for r. And then for dr dt, how fast the radius is changing, we're going to plug in the 1 foot per second that we were given earlier in the problem. So now let's multiply all of this out together. The 2 pi times the 4 will give us an 8 pi. I'll just leave my answer in terms of pi. Pay attention to the units here though, because we have feet times feet divided by seconds, leaving us with feet squared per second, which makes sense because we are asking how fast is the area changing. Our answer should be in feet squared per unit of time. Here we have some strategies outlined to help us when we're solving a related rates problem. I'm going to go ahead and jump into example 4 by taking the first strategy and drawing a picture. We have air being pumped into a spherical balloon. So we have a balloon that looks like this. They tell us that the air is being pumped in at a rate, that's a derivative, of 4.5 cubic feet per minute. So they have given us the rate of change of the volume. They have given us dV dt. We are being asked to find the rate of change of the radius. So yes, this sphere does have a volume, but it also has a radius, when the radius is 2 feet. So we're being asked to find how fast is the radius changing. We want dr dt when r is equal to 2 feet. So first we're going to have to start with the formula for the volume of a sphere. We're dealing with volume and radius here, so the equation that relates those, because we've already done, I'll point out, we've drawn the picture. We've already written down any numerical information and what we wanted to find. So we've done 1 and 2. Now we're going to write an equation that relates these. So for our case, that equation would be the volume of a sphere, which is 4/3 pi r cubed. Now that we have that equation, we're going to go on and do step 4, which is to differentiate both sides of this equation. So we're going to come in and take the derivative on both sides. Notice I've gone ahead and pulled the constant coefficient of 4/3 pi out from the right side of the equation. On the left side, the derivative of v is simply dv dt. On the right side of the equation, this constant stays here. We're going to need to use the power rule. We'll bring the exponent of 3 down. New exponent on r will be 2. And chain rule tells us to multiply by the derivative of r. So now I'm just going to simplify because I can cancel these 3's here and be left with dv dt is equal to 4r squared dr dt. So now that we have this equation, we can go on to find dr dt that we're looking for. So remember what we are looking for in this problem. We want to know what is dr dt when r is equal to 2. So, and we already knew that dv dt is equal to 4.5 cubic feet per minute. So we know what we can substitute in here. 4.5 cubic feet per minute. That's how fast this volume is increasing. We're interested in finding out information at the moment when the radius is 2 feet. So I'm going to be replacing r with 2 feet. And dr dt is what we're trying to find. So I'm going to simplify the right side of the equation. 4 times that 2 feet squared is going to give us 16 feet squared. And then to solve for dr dt, I need to come in and divide both sides of this equation by 16 feet squared. Us with, I'm not rounding this is 0.28125. And let's take a quick look at what units we're left with. We had 4.5 feet cubed divided by feet squared. So two of those feet squared will cancel, like a foot and a foot will cancel and just leave us with a foot. And then we still have the per minute. And this is our final answer for dr dt. And we're talking about the rate of change of the radius, so it should be measured in singular units per measure of time. One thing I want to point out about this example is notice that we did not plug in any of this numerical information until after we had taken the derivative. So when we started plugging in values is right here. Right here we started plugging things in. But that did not happen until after we had already taken the derivative. So when you start these problems, the first thing that you're thinking about needs to be, what equation do I need to start with in order for me to take a derivative and be able to see whatever it is that I'm trying to solve for or what I have some information about. In example 5, we have a hot air balloon rising straight up from a level field. We're also told that it is being tracked by a rangefinder 500 feet from the lift-off point. That gives us this horizontal distance here at the bottom of this right triangle. And I do know it's a right triangle because this tells us that this is going straight up from a level field. They go on to say, at the moment, the rangefinder's angle of elevation is pi over 4. So we are talking about the angle in the triangle right here. I'm going to go ahead and call that angle theta. They tell us that at that moment that this angle is increasing at a rate of 0.4 radians per minute. How fast is the balloon rising at the moment? So what we want to find is how fast the balloon is rising. So the balloon has a certain height above the ground that is changing as the balloon goes up. It's increasing. We want to know how fast is it increasing, how many feet per minute. We want dh dt. And we want it specifically when this angle here, theta, is pi over 4. We want it when the angle theta is pi over 4. And they also told us, by the way, when that angle is pi over 4, the angle is increasing at a rate of 0.14. So at that moment, I do know that d theta dt is 0.14. So we need an equation that's going to relate the information that we have. We have information about the height, or we want information about the height. We have information about the angle theta, and we also have this side of this triangle here. So back in trigonometry, we learned how when in a right triangle, we can relate information about an angle, its opposite side, and the side adjacent to it in the triangle. And we can do that using the tangent function. Tangent of that angle theta is going to be opposite over adjacent, which is h over 500. To help make this equation a little bit easier to work with, please do note this is the exact same thing as 1 over 500 times h. Now, in order for us to find the h dt, we're going to need to differentiate both sides of this equation with respect to t. And remember, we always take the derivative before we plug in any values. On the left side, the derivative of tangent is secant squared. And because we have that theta on the inside that is changing, we will pick up a d theta dt. On the right side of the equation, we have that constant of 1 over 500, and the derivative of h is dh dt. I want dh dt under certain conditions, so I'm going to go ahead and plug in theta equal to pi over 4 and d theta dt equal to 0.14. Now I would need to multiply both sides of this equation by 500 in order to get the dh dt by itself. So I'm multiplying both sides by 500 so that this will cancel out. I'll pick up a 500 on the right-hand side. And the value of secant pi over 4 is root 2, which we will then still have to square and multiply by 0.14, which leaves us with our final answer for dh dt as 140, and this will be measured in feet per minute. In example 6, we have an example with a police chase. A police car is approaching this right angle intersection from the north, and he is chasing this speeding car that is now heading east. And they give us some particular distances at a certain moment in time. But generally speaking, I'm going to call the distance from the policeman to that intersection, I'm going to call that distance y. And I'm going to call the distance from the intersection to the speeding car x. Note that both of these variables are changing, so there is a dy dt, and there's also a dx dt. I will point out that dy dt has to be negative because y is decreasing, while dx dt has to be positive because x is increasing. The distance between that car and the intersection is increasing as he continues to drive off to the east. Now back to the problem. They say when the officer is 0.6 miles north of the intersection and the car is 0.8 miles to the east. So we are specifically talking about the moment in time when y is equal to 0.6 and x is equal to 0.8. That's the distance for the officer and the speeding car, respectively. They tell us that at that moment, the officer uses his radar to determine that the distance between him and the car is increasing at 20 miles per hour. Now, that's a new variable. That's the variable for the distance between him and the car. Well, the distance between the officer and the car is this distance here that I will now come in and call z. So at this moment, when y was 0.6 and x was equal to 0.8, the officer calculated that the distance between him and the car is increasing at 20 miles per hour. So he calculated that z is changing at a rate that dz dt is 20 miles per hour. They go on to say that if the officer is driving 60 miles per hour at that instance, that gives us how fast y is changing. It gives us the rate of change of y. So that tells us that dy dt is equal to negative 60. and it's negative because y is decreasing. I'll add that up here. They're asking us, how fast is the driver going? What we want is dx dt. We want to know, what is the speed of the driver? How fast is this distance changing? So what equation can we use to get started and relate x, y, and z? Well, we're working in a right triangle, so we can use Pythagorean's theorem. Now that we have the equation, we need to come in and take the derivative of it with respect to time. Remember that all three of these variables are changing with respect to time, and so all three of them have a derivative. We will need to use the chain rule every time we take the derivative of a term in this equation. There's a 2 that shows up in every single term, and so we can divide everything by 2 in this equation just to simplify and make this a little bit easier to work with. So now let's look at what we have and what we want. Remember, we're trying to solve for dx dt. So I want dx dt. Let's go see what we have all in the equation. So what they have given us so far is they gave us x, so we have this part. They gave us y, we can plug in there. We have dy dt, that's the speed of the cop. We have dz dt, that's how fast the distance between the cop and the driver are changing. But what we do not have is we do not have z. And we would need to know that because remember, we're trying to solve for dx dt. So I want this to be the only unknown once I start plugging things in. Remember, we don't plug anything in until after we've taken the derivative. Now that we have taken the derivative, we could start plugging in, but we have nothing to plug in for z. We do not know what z is when, at the particular moment, when y is equal to 0.6 and x is equal to 0.8. So how could we find it? Well, even just looking at this picture, if we're talking about the moment when x is 0.8 and y is 0.6, I could use Pythagorean's theorem with no calculus at all to solve for what z is equal to, which is what I'm going to do right now. To get that z is equal to 1. So now we had to go find in all this list that they gave us, the value of y, the value of x, the value of dz dt, the value of dy dt. We had to go find that z was equal to 1, and now we can go plug in what we need in order to finish solving this equation. So now I'm going to continue simplifying. I'm going to add this 36 to the other side of the equation in order to give me 56. And then we are going to divide both sides of the equation by 0.8 in order to find that the driver is driving at 70 miles per hour.